Hello, this is Dr. Mike Kawuki, and we are continuing on a series of lectures on our course, CH103, and this is chapter 14 on the topic of acids and bases. So we're going to look at the definition and talk about the strength and how do we measure the acidity that is on the pH scale, and then we'll go on to the calculation of pH. Then we'll finish off this section with bases and polyprotic acids. Let's talk about the first definition of an acid and a base. This is actually the definition by the first discoverer, that is Arrhenius. He came up with the idea, or with the definition, that acids produces hydrogen ions. If you look at this, acid is a source of hydrogen ions that is in aqueous solution, and bases are the source of hydroxide ions. So basically the species that we are referring to here is the hydrogen ion species, H+, and hydroxide ions is OH-. So this definition is a very basic definition, but it has certain limitation. So it's not as wide-ranging as one would think of acid and bases today. So there's another definition which is more encompassing, which is from two scientists, Bronsted and Lowry. So it's called Bronsted-Lowry model. And the definition of acids from Bronsted and Lowry is acid is a proton donor and base is a proton acceptor. So it's basically based on the species proton. And we'll see what that means in the examples that we are going to look at. So let's look at a typical reaction of an acid in water. This is HCl reacting with water. Notice that we are writing this reaction in the equilibrium sense, as we have already studied this topic before. So water, pure liquid, dissolving HCl. This is hydrochloric acid in solution, and it produces the hydronium ion. Now this is the acid species, and we'll find that hydronium ion is essentially given as H+ in the abbreviated sense. So at times we're going to be using just H+ instead of hydronium ion. So here we refer to as hydrogen ion, but in actual species in solution, it is actually hydronium ion. And the other is chloride ion. We're familiar with that. So if you look at the molecular model shown here, you see the molecule, that one hydrogen. You see here the hydrogen that is essentially in the acid is now transferred to be in water. So this is the new molecule, or the new species, which is hydronium. So you're left with just chloride ion and H3O+. So remember the term hydronium ion, which is H3O+. Now, yeah, sorry about this slide. It's a little bit messed up here, but the reaction is the generalized reaction of an acid in water. So if you have an acid combining with water, you'll form the hydronium ion, and it's an ion. Now we label that in terms of the pairs, and we call that conjugate pairs. So if this is the acid and this is the base, why is this an acid? This is a proton donor. This is a proton acceptor. So we are using Bronsted-Lowry definition. Okay, Bronsted-Lowry definition. Acid is a proton donor and base is a proton acceptor. So here is the new species, hydronium ion. So the hydronium ion is actually a species which is an acid. How do you know an acid? Imagine it going this direction. If this direction is the reaction, you'll find that this is going to be donating a proton. This will be receiving a proton or accepting a proton. So you can think of it in that sense. So an acid here, this is its conjugate acid. A base here, this is the conjugate base. And these are the terms that are used in that. So we're going to be using the acid and its conjugate, or base and its conjugate, as we go on from here. Now, that leads us into calculating this term, which is the K value. We already understand that equilibrium constant is the concentration of the products divided by that of the reactants raised to their coefficient. So if you have an acid dissociation, we can write the equilibrium constant in the same manner that we have learned in the previous chapter. So notice that it'll be the concentration of the products, which is hydronium ion and the anion, divided by the concentration of the acid. Remember something, water is not included. Why? It is because water is a pure liquid. So just remember that. That's what we've already learned from the previous chapter. Let me just take this up so that you don't get confused with that. So so that is the equilibrium constant for the dissociation of an acid, and you will see here that it is generalized in this form. Ka is equal to H3O plus, which is the product of the dissociation of the acid, and then the concentration of the acid itself before dissociation, or the initial concentration, or the concentration of the acid undissociated, and is given the subscript A to designate that is an acid dissociation constant. Okay, let us write the simple dissociation or ionization reaction for this acid. Let's try this one, HCl. Okay, if we ignore water, this is how we're going to write it. So in a very simplistic sense, it'd be H plus Cl minus. All this in aqueous, remember, aqueous. Okay, and likewise here is aqueous and aqueous. Okay, so I can write the same here. There is one proton here, so this will be the acid, and likewise here there is 3 hydrogen here, so you will take away 1 hydrogen to be a proton. That will be dissociated from here. So let's see if that shows up in, okay, I've shown it here in the first one. Sorry, I've written this in the extended form with the water. You can see that HCl breaks in water or dissociates in water to form the hydronium and the chloride ions. Let's go to this is the abbreviated one, which I showed in the earlier slide. So just HCl breaking into it. So this, we tend to use it throughout this class, this lecture, but be mindful that it is the extended and the proper format for that. So let's look at the this acid here, which is acetic acid. So this is a single proton here. Notice the difference. There are 3 hydrogens here, but this is the single hydrogen. So these are not acidic hydrogens, but this hydrogen here is the acidic. So you see it dissociated and the rest of the hydrogen still there. So you have to distinguish between the acidic hydrogen and the non-acidic hydrogen when you're looking at a structure like this of acetic acid. Let's go to another form of the acid. You see here in aluminum. Okay, I think that's the one of the types of acid that is shown in here. Let me go to the equation, showing here the equation. So you see here that's aluminum with 6 water molecule. 6 water molecule, that's aluminum 3+. And most of you should be familiar with this. Aluminum belongs to group 3A in the periodic table, and they have the valency or the charge of +3. So when they combine with the water molecule, water is still neutral. It doesn't have any charge. So all those 6 water molecules are attached to aluminum without changing the charge. So it's still 3+, but they're all connected to the same aluminum cation. Now, if you are looking at this, these are all water molecules. This water can actually dissociate into H+ and OH-. Not all at once, but one of them can do that. The reason is that because of the very high charge, that is +3 of the metal, it will attract the oxygen, which is electronegative, and thereby allowing hydrogen to be loosely bonded, that it can be dissociated. So that's exactly what you see here. So you see one hydrogen coming off, and if one hydrogen comes off, this whole entity here is just one less hydrogen. In other words, this entity here is one less hydrogen. So if you take out one less hydrogen, you'll be left with 5 complete water, and then 1 with just OH-, but we don't say it's OH-. The reason is that still there is a 3+, so with the 1-, you'll be left with this charge here, 2+. So that's the overall charge. So it is a proton donor. You see here, that's an acid. And this is a very unique type of acid which comes from a metal complex. Okay, so that's a metal hydrogen, metal water complex. Okay, now let's go to the definition that we have looked at in the Bronsted-Lowry model. If you look at this definition, a proton acceptor and proton donor. Now let's look at this. This is ammonia gas. So this we're talking about gaseous phase. Ammonia gas and HCl gas. And then you combine the two. This is a very strong, highly exothermic reaction, and you'll form ammonium chloride, solid. So no solution, in other words, no water is involved in here. So without any water at all, you see the reaction taking place, and this still is an acid base. What is unique about this? You don't see any water at all, and also you don't see any hydroxide species ever seen in here. You don't see any of this. So this is one advantage of the Bronsted-Lowry definition compared to Arrhenius definition, because here in Bronsted-Lowry you can say that an acid is a proton donor. Proton donor, and this is the proton acceptor. And that means this one is the acid, right? And this one is a base. So that's one reason why this definition is a lot more wide-ranging and encompassing compared to the Arrhenius definition. So you'll see a lot of this in the forthcoming discussion. You'll see more of this type, where you don't see any hydroxide at all, but you will just see the movement of protons. That is proton acceptor and proton donor and proton acceptor. Why is this a proton acceptor? I think you can go back to the Lewis structure. If you look at the Lewis structure, it has three hydrogen in the trigonal bipyramid. Trigonal pyramid, and 2 lone pairs. Remember that. So this is where the hydrogen plus actually comes and occupies. So it comes here and occupies this lone pair to give this species an overall NH4+, which is what you find in here, NH4+. Okay, and now let's move on to the strength of an acid. How do you define the strength of an acid? Well, we've learned a little bit from chapter 13, and that is if you have a dissociation which is further to the right, that means is designated by high or large, sorry, it should be large K value. If it's going to the left, it is the low K value. So we're going to bring that notion here. So in a strong acid, what we say is that equilibrium lies far to the right, and therefore, notice this is going to be a new sort of description. So it yields a very weak conjugate base. So in other words, this species here that is formed is weak. Weak in what sense? Compared to water. Okay, compare to water. Okay, CF there is more. So it is a weak conjugate base, meaning that when this forms, if it's weak, it will not react with water. It will remain as is. Okay, let's look at the other one. Weak acid. The equilibrium lies to the left. So this is different. It gives you a strong conjugate base. So in other words, the conjugate base, let's just say A minus, from here, it's going to be, it will react with water. So the question is, what sort of reaction will it undergo? So we'll be looking at that, but not just yet. So what we're seeing here, the strength of the acid is determined by the equilibrium. So if you have a large K value, that means it's a strong acid, and if it's a weak acid, it's a low K. So one other way we can say is that if you have a strong acid, it will dissociate completely. Dissociate completely. Okay. What about the weak acid? It will only have a partial dissociation. Okay, partial dissociation. Sorry about my pen. Okay, let's go on to. So here is a description of or a picture to show the two kinds of acid for strong and weak acid. The strong acid on the left, you'll find that if you start with the acid group here, HA, when it dissociates, there's hardly an HA left in the product. You see that? All has broken into H plus and A minus. So if the acid is a 1-to-1 type of acid, you have the same ratio, 1-to-1 of H plus and A minus. Now let's take the HB. If it's a weak base, a weak acid. Weak acid, you start off with this at the beginning, and guess what? You're still left with the majority of the product still HB, and only a small fraction are H plus and B minus. So that's the difference between the strong and the weak acid. So here is large K. K is large. And this one is K is small. Okay, I should say Ka. Ka. All right, so this is a summary. For strong acid, Ka is large. The reaction is far to the right. So in other words, the ionization is almost complete. And the concentration of the acid, H plus, is almost approximately the same as the concentration of the original acid. And A minus, that is the conjugate base, is weak. That is weaker than water. In contrast, weak acid, the Ka is small. Equilibrium still far to the left. That means more of the acid are still in the final mixture. And then H plus is much, much lower than HA0, which is the original concentration. So only a very small proportion is dissociated. And then the conjugate base is much stronger than water, so it should be able to attack water and react. Now, what we're dealing with so far is the one proton acid. We also can have diproton, so we call that diprotic. The one proton is called monoprotic. Monoprotic acid. So for two protons is diprotic. An example of that is H2SO4. And you have other acids, a group of acids called oxyacids. These are acids that has oxygen bound to a central atom, and then also an oxygen to the hydrogen. So examples of these are nitric acid, phosphoric acid, and also is sulfuric acid. These are all oxoacids. And then we have the organic acids. Organic acids like acetic acid, the example we've looked at, has this sort of functional group. We call them the functional group. It has a carbon atom backbone. All organic acids are carbon-based, and it has the structure at the end of that chain, or the functional group. So an example is acetic acid, which is this one. Note that acetic acid was written in this form. Okay, so it's the same. We write it in this form because it shows the hydrogen clearly that is acidic. So what I'm saying is that these hydrogens are non-acidic compared to that one. So this is the acidic hydrogen. These are non-acidic hydrogen. Okay, so same thing here in benzene with the acid group. We call that benzoic acid. So this is the acidic hydrogen, and this is the common normal bonded hydrogen that are not acidic. And then you have the hydrohalic acid, the halides, acids of the halides like HCl, HBr, or HF. So all those are hydrohalic acids. We start those acids by naming in hydros. So for example, hydrochloric acid, hydrofluoric acid. So acidic proton is attached to an atom other than oxygen. So in this case, it's the halogen. So I mentioned about monoprotic acids only contains one acidic proton. Some example of acids that we can regard as monoprotic, for example, like hydrogen sulfate, phenol. These are uncommon from what we have generally studied, but you can see that it just have one proton in this example. And of course, you see all this hydrohalic, monoprotic, and so as acetic acid that we have looked at. All right, vinegar contains acetic acid and used in salad dressing. If acetic acid was strong acid instead of a weak acid, would it be safe to use vinegar as salad dressing? Definitely not. Okay. Why? It is going to ruin our digestive system very, very easily because of the nature of the acid. So yeah, that's not why we use strong acids like acetic acid, like HCl in food. Okay, these are examples of some of the acids that we will be studying. Let's just look at a few of this. Hydrofluoric acid, HF, that's 10 to the minus 4, its Ka value. Let's look at HCN, HCN, that's hydrocyanic acid, that's to the -10. These are very low. So you can sort of see the categories. So this is one group, relatively low, HSO4, which is hydrogen sulfate, chlorous acid, and monochloroacetic acid. And then you come to this category here, which is the next group. This is the much lower, that next level. That is, you can see 10 to the -4 to the -5 range. Hydrofluoric, nitrous, acetic acid. And then you come to very weak acid. You're looking at hydrocyanic, ammonium, and phenol. Now, you wouldn't see these acids, remember. Why? These are very strong acids, so their K values are really large. That means greater than 1. So you don't see that. So this is a typical table of weak acids. Very weak and intermediate and mildly weak here, right at the top of this. So this is in the increase in the acidity strength, and you can see that it relates to the equilibrium constant. As you increase the Ka, you increase the strength of the acid. Now, some molecules, and water is an example, we call them amphoteric. Amphoteric means it can both act as an acid and a base. So water is one molecule that behaves as such, that it can behave as an acid and a base. And you will see some of the examples here later on. So for example here, water, you can see that one molecule dissociate to produce hydronium and hydroxide. Acid, okay, that's an acid species. This is a base species. We know that a base, it has hydroxide ions. Now, then why do we not see any clear contrast when you're looking at water? The reason is that these two concentrations are pretty much equal. They counterbalance each other in water. So we don't see water to be either acidic, neither acidic, nor basic. So that's why we see water as neutral. So an important relationship here. When you write the K of this value, of this K, equilibrium will be the concentration of this H3O plus and OH minus. And we know that water is a liquid, pure liquid. You don't have any denominator in here. So this is exactly the equation. We call that Kw. So the subscript W is for water. That is the ionization product of water. So notice that ion product of water is Kw, and it's a constant, and you'll see the value given in there. Just before we move on, you can see that you can write it in the abbreviated sense. Without this as a full hydronium, you can just write as hydrogen ion. So what is the value of the Kw? This is a very important value. So 1.1 times 10 to the power of -14. And you will see how unique this value is in most of the calculation we are doing. So when we look at this and we solve the equilibrium concentration, let's say, of water at 25 degrees Celsius, so what do? We can solve this. H plus multiplied by OH is equal to 10 to the 14, which is Kw. So this should be the same concentration, or X and X, if you draw the ICE table, and then you solve for X, you take the square root. Lo and behold, this is what you get. So the concentration of OH, excuse me. So the concentration of OH and H plus is the same for water, and that is 1 times 10 to the power of -7 moles per liter. So this is a generalization we can use, and that is If the concentration of H plus and OH are equal, that means the solution is neutral. If H plus is greater than OH concentration, acidic. If OH is greater than H plus concentration, that's basic. Right, I look at the outer ionization of water. Let's look at this one here. Using Le Chatelier's principle, predict whether the following reaction is exothermic or endothermic. So look at this. At 60 degrees, this is 1 times 10 to the power of minus 13. And remember, we know at 25 degrees, okay, 25 degrees, Kw is equal to 1 times 10 to the power of minus 14. And then we can calculate the concentration of the species in there. So if you look at the equation, H plus and OH is going to give you the K value, which is 10 to the 13, and you come up with a less number of the molarity, which is 3 times 10 to the power of, sorry, not less, sorry, greater. That is 3 times 10 to the power of 7 moles per liter. Okay, how do we measure the acidity? It is measured by the pH scale, and pH is essentially related to the potential of hydrogen ion. That's the what P and H represent, potential and hydrogen ions. So it has to represent the solubility of the solution of acidity. So in the log scale, this is the equation. pH is a log function. It's minus the log of the concentration of hydrogen ions, or minus log of the H3O plus, okay? H3O plus, and that is hydronium ion. Okay, so what is the pH of a solution with 10 to the power of minus 7 H plus? This will be the pH, minus log of the concentration. So this is the concentration. Take the log of that. It'll be a negative number. That is number minus 7. And with a negative, it'll give you the positive value. Now, one important thing about significant figures. If you have a concentration in 2 significant figure, 1.0 times 10 to the power of minus 9, that's 2 significant figure, right? Now, in terms of pH, you have to record the pH into 2 decimal places. Why? The reason is that this represents the number of significant figure in the pH reading. This will represent the number of significant figure in the concentration. So the number of decimal place in the pH reflects the significant figure. 9 here is the exponent, which is the mantissa. Okay, I think that's, you can check that in maths. That's the power, basically, the power to the power of 10. So this doesn't carry the significant figure representation. Significant figure comes to the number of decimal points that you use in here. So the log scale for pH ranges from 0 to 14. You can see here 0 to 14. So the lowest pH will be 0, and you're looking at about molar HCl. That's pH of 0, whereas pH of a molar NaOH is 14. So in other words, that kind of reflects the scale in which we measure pH using the pH scale. Now, in relation to the pH, we can also use pOH. Essentially the same relationship that we do. Instead of minus log of hydrogen ions for pH, this will be minus log of the OH ions. At the same token, we can also write down what is the pK pK is minus log of the Ka value. Say, for example, if you have the Ka of the acid, or you can have the pKw if it's water. So you can also be looking at the potential of the constant equilibrium constant value. Now, pH meter is a device that we use for measurement of pHs, and the construction of a pH meter includes electrodes. Actually, you have two electrodes. One is the working electrode, and you have a reference electrode. Okay, in general, that's what we have in a pH meter. And the potential difference between these two, that is the voltage, let me just put a voltage sign between these two, is what essentially measure the pH in general. Now, one thing about the working electrode in pH meter, it actually has a membrane, and that membrane is glass, and the glass membrane is what provides the sensing, or the sensor that will be able to determine the pH. So in that glass, outside the glass, we have your analyte. So this is the, let's say this is the solution we are, and then inside the glass you have, let's say, electrolyte solution, KCl, with some, let's say, a little bit of the acid. So you have a concentration of H between the inside of the glass and the outside of the glass. And that change in the concentration, or the gradient in concentration, is what determines the voltage. So that's the construction of the pH meter. And here's a pH meter reading. So you can see here the vinegar is showing a pH of 2.36 here. So this is a pH probe, and the glass tip, you will see it's sort of encased in there. It's a very sensitive tip. So you do not try, we do not really handle that very harshly, because it's very sensitive, and it monitors the changes in pH. So this is an acid, vinegar. So if you look at the next one here is 11.37. You look at this one is an ammonia solution. So ammonia solution is basic and vinegar is acidic. Okay, one example here on calculating pH and pOH. Let's just look at that. So calculate the pH of this solution here. So if you're given the hydroxide concentration, remember, you can find the hydrogen ion concentration. The reason is that pH is determined by the concentration of hydrogen ion. So you calculate the hydrogen ion using Kw. So Kw over OH will give you this value, and then you can convert that into pH, and that gives us the answer, 11.00. That's the pH. And once again, the 2 significant figure here, that's why you have 2 decimal places here. Okay, pOH will be minus log of the OH concentration. So we have the OH here, and we can substitute and get. So you will see that pH and pOH add up to be 14. So that's an important number, which is pKw. Okay, that's the second example, and we have this. The pH is 0 and POH is 14. So that's the acid, which is a very strong acid. You can see here that the acid has a pH of 0. So that leads me to this equation that I've just shown you. pKw is equal to pH plus POH. Okay. And we can calculate the POH and we can calculate the pH, or in that sense also work out pKw. So let's look at this example. The pH of a human blood was measured to be 7.41 at 25 degrees Celsius. Calculate pH, POH, H plus, and OH. Let's look at that. Since that is the relationship, we can find, let's say, work out the POH. So POH is equal to 14 minus the pH, and that is this value here. To find H plus, we look at the definition. So converting that to concentration, you have to take the anti-log. So notice the step. 7.41 is equal to minus log H plus. So log of H plus, take away the negative sign, it'll be minus 7.41. And then take the anti-log of that. And then you take the anti-log of that, that will be the answer. So in this case is 3.9 times 10 to the power of minus 8. Notice when you're taking anti-log, that's the relationship you're actually performing. 10 to the power of minus 7.1. And that will give you the final answer. Now you can see why this is 2 decimal places. This is 2 in a figure. All right. And then you can work out the same for the concentration of base, and that will give you the value. Okay, in the last slide here, I'll leave it as an exercise. So this is a good exercise. So what you will do, sorry, that slide is already showing up. I don't want it to show up. Given the pH, complete this table. And complete this table just given the OH. And then complete this table given the POH. And likewise given that. So this is a good exercise. I'm not going to go through it, but I'll let you try that on your own. And fill in the table. The answers are already given in here, so you can check it out with the answers. All right. So that will complete this set of notes. And thank you for listening.